Oh, hey. Hey, is it you, Brandon? So, you see, today's Valentine's Day and your special someone told me that I should have a little date with you today. Just a few little seconds, and she wanted me to tell you something, so come on, let's come to my fireplace and we are going to talk for a little bit. So Brandon, I made it nice and romantic for the two of us. So Erin asked me if she could consider your Lagrangian this Valentine's Day, but with friction. She would like to quantize your manliness this Valentine's Day. She would like to interchange limits without any restrictions. And also she would like to do something really crazy. She would like to expand your non-analytical function into a Taylor series. So Brandon, once again I'm wishing you a nice Valentine's Day, and don't forget to spend this special day with your loved one. Mine is Anton right here, our dog. See ya. Good morning, fellow mathematicians. Welcome back to another video. Today's special day, Valentine's Day. Don't forget to spend the time with the people you appreciate the most. I appreciate ya, my boys and Chris out there, and that's why I'm going to spend a few minutes with you today. Love you guys. What are we going to do today exactly? We are going to derive the equations of motion for a cardioid. And after that, the area under this cardioid curve. If you ask yourself what the hell a cardioid is, this is a cardioid. So, right here you see here's a little GIF or something. There should be something. I certainly can't see anything, but after doing the editing, I can certainly see something. Yeah. So how would you go on with something like this? There are definitely many ways out there to derive something like this, but we are going to do it my way using some coordinate transformations and stuff like this. That's why it's going to take quite some time. So at first I would like to just take a look at a certain situation in this cardioid structure. So let's say at first we have a circle with a certain radius rho centered in this coordinate system. So the center of this circle is right here in the center of the coordinate system. It has a certain radius rho. And on the arc of this circle there's going to roll another circle around. And one important thing to notice is that this circle rolling around the other circle has to have whatsoever the same radius as this one right here. If it wouldn't have the same radius, then it wouldn't form a cardioid in the end. It would form something different, a certain different geometric structure. So this circle right here also has a radius rho, meaning the line connecting our coordinate system center and the center of this circle is going to be 2 rho, the magnitude of this line right here. Okay, but there's also this point, let's call it P, okay? It's going to lie somewhere here on the circle, which is going to trace out our cardioid in the end. And this P has a certain x and y coordinate in this initial coordinate system, okay? And like I said, we are going to do some coordinate system transformations to find out where this point P is going to be in a different coordinate system, such that we can easily find out where this point P is in our initial coordinate system. Okay, let's do some geometry, just some easy observations. Let's say we are looking at a different situation, okay? Let's say we have this right here at the moment, so this right here is rho once again, and our initial situation would be this right here. Both circles, oh, what a beautiful circle, what a great and beautiful individual. Oh, it looks so dope. Yeah, we have this circle right here lying exactly on our coordinate system. So this line right here goes right through the center of our circle, meaning this line right here is rho. So where's our point P going to be? It's going to be somewhere here. So exactly lying on this x-axis. Okay. And after that it's going to roll around a little bit. So maybe after some time, our point P is going to wander from down here to here, for example, okay? It's now up here. Once again, this line connecting this and that is going to be 2 rho, and we have our point P right here. There's going to be a certain angle being traced out right here. Let's call it phi. And one important thing to notice is that this arc length right here, okay, so the distance we have traveled on this other circle is going to be the same as this distance right here. That's why I've drawn this little sketch once again. So we are rolling this around, and well, this arc length is going to be the same as this one after traveling a few centimeters, for example. Okay, now we can take a look at this differently. So we now have this thing right here, okay, and then we have our circles like this right here. Okay, this right here is the center of this circle, this right here is the center of this circle. What you can easily show by implicit differentiation is that, well, this is a line connecting the center and the arc of the circle, meaning we can have an actual tangent line right here. And this tangent line is also going to be tangent to this thing right here, meaning we have 2 right angles right here. Okay? But like I said, we have a certain point P right here, and this arc length being traced out is going to be the same as this arc length being traced out. Meaning we can actually draw a line from right here, so this tangent point, to this point, and then we can connect the center and this point right here, and we are going to have a certain length right here. This length right here is going to be the same as this length right here. Then we can draw this line right here. This is just some intuitive arguing right here. And then what you can notice is if you connect those 2 points right here, those are going to be right angles once again. No, this one right here. Where am I going with this? If you do some more geometry, you can find out that this angle phi is exactly the same as this angle phi up here, and we are going to need this later in the game. So that was just some initial observation. That's an absolute beautiful sketch up here. And what we want to do at the moment is find out where our center of this circle is going to be all the time regarding this coordinate system right here. Let's say this center up here is called C, and it's going to have a certain x and y coordinate. For reasons that will become apparent in a minute, we're going to call this coordinates A and B, for example. Okay, what are those A and B coordinates exactly? Well, if we draw a little triangle into here, you know that this thing right here is 2 rho, this length. Then we have a certain angle phi being traced out, and now we can just draw this line down here. Up here is the center of the circle, C, and well, that's the right triangle. Our center, C, has a certain x length, let's call it x, which is nothing but A in this case, and a certain y coordinate, which is nothing but B. How can we find out those A's and B's? Well, just using trigonometry. So you see 2 times rho times the cosine of phi is going to give us A, and the same spiel with the B coordinate, just with a sine instead of a cosine. So that's just some easy trigonometry. You should see where this comes from. So we are going to have 2 times rho times the cosine of phi, and 2 times rho times the sine of phi. Now we are done with this. Why have I done that? Well, we are going to make use of this center right here, and we are going to place a new coordinate system up here in the center. So the center point of this circle is going to be the center of our new coordinate system. How does this exactly work? Let's say we are having an initial coordinate system, okay? So we are going to have this coordinate system, and for simplification purposes, let's say here in the center, some person A, let's call her Alice, person A, Alice, is going to watch from this point, okay? And she's looking at a certain point P with an x and y coordinate, okay? So that's our y coordinate and that's the x coordinate. But let's say she has a friend, B, let's call him Bob, for example, and he's watching from this position right here. meaning Bob is watching from this position. But in his coordinate system, the point P is going to be somewhere else. Our point P is going to be a point P prime, for example, and it's going to have an x prime and a y prime coordinate. So what we want to do, we want to find out where our point P prime is going to be in Bob's coordinate system. That's what you call translation, if you have ever done physics or elementary geometry. Let's say our point P, for demonstration purposes, lies at, let's say 3 and 3, okay? So this sketch is actually quite accurate. Then we have to take a look at how much this coordinate system of Bob is shifted to the left or right, up and down, with regards to Alice's coordinate system. Let's say this length right here is A, the shift to the right in this case, and this length right here is B, the shift up. That's why I've called it A and B. Maybe you can already see why I did this. Okay, let's say Bob's coordinate system is shifted 5 units to the right and 2 units up, for example. Okay, it really doesn't quite matter, it's just for demonstration purposes. Then, since this sketch is quite accurate, our x prime coordinate is going to be somewhere in the negatives right here. So if we just place this line right here, that right here is our x prime coordinate, okay? And it's going to be somewhere in the negatives. How are we going to acquire this negative coordinate? Well, what we can do, we can just say we are subtracting A from our x coordinate, okay? And the same spiel with this shift in B. So 3 minus 2. Then we are going to end up with -2 and 1. So this is just something intuitive you can actually find out. So you see our y prime coordinate is going to be somewhere in the positives up here. So that actually works out. And this is how it's always working with translations. Meaning we can express our x prime and y prime coordinate in a new coordinate system as nothing but the initial xy coordinate minus our shift of the coordinate with respect to the initial one. And yeah, this is basically it. This is what you call translation, and you can, well, just advance this to even higher dimensions. If you have a z coordinate, for example, then the z prime coordinate would be nothing but z minus z, for example, the shift in the z coordinate region. And yeah, this is basically it, and we're going to work with it. Meaning, now we are going to place a new coordinate system up here, and then we are going to see where our point P is going to be in this new coordinate system all the time, and we are going to call this point P prime. And then what you can actually observe, if we know where our point P prime is going to be in this new coordinate system all the time, then we can just solve for x and y, meaning adding this vector on both sides, and we can actually find out where our point P is in this initial coordinate system all the time. So this is absolutely brilliant, and this is what we're going to do next. So there was already quite a lot of input probably for you guys. So if you didn't understand something, then just go back a little bit and see if you can understand it. We've talked about a lot of concepts right here. So now our main goal is to find out where our point P prime is in this new coordinate system, this dotted one up here, which is lying right at the center of our outer circle, C. Now we can just make use of trigonometry to find out where our point P prime is, because it's an easy feat now, because, well, dealing with something that we can evaluate from the center of a coordinate system is really quite easy most of the time. Okay, how can we manage this? Well, it would be crazy good to find out what this angle right here is. Let's call it theta, because if we would find out this angle theta, we can draw a little line down here and we can manage to get a little right triangle. And with this we can easily find out P prime once again. The only thing that's pulling us back at the moment is this angle right here. We don't know what this angle is. Let's call it alpha up here. So if we would know alpha, then we can just simply construct our angle theta right here, because, well, 180 degrees, pi is made up of alpha plus phi plus theta. Let's take a look at another sketch. Okay, we have this angle phi right here and this angle alpha. And don't forget, this line right here is our x prime axis, you could say. One thing that's cool about translation is that our x prime axis is going to be perpendicular to our y axis that we have right here. Meaning if we just extend this line down here, that's our y axis, we can actually draw a little right triangle here. With this right here being another angle, let's call it gamma for example. Then in the beginning we have also found out that this angle right here is going to be phi. And don't forget, this right here is the center of our original circle that's lying right here. Meaning if we just extend this line, we're going to get something like this. Okay, here's the center of the coordinate system, that's the x-axis, that's the y-axis, meaning gamma plus phi is going to make up pi over 2 exactly. So that was easy to see. So you see that's the right triangle, not a right triangle, that's the right angle right here. Also we have this right triangle right here, meaning gamma plus alpha plus, well, pi over 2 is going to make up pi. Okay, what we can actually do, we can solve this thing right here for gamma for example, meaning pi over 2 minus phi is nothing but gamma, and now we can substitute gamma into here, meaning, okay, also we can just subtract pi over 2 on both sides to get rid of this right here. Okay, we are going to get that pi over 2 minus phi plus alpha is going to be pi over 2. Okay, easy peasy, melon squeezy. Now we can just subtract pi over 2 on both sides to get that phi, negative phi plus alpha is nothing but 0, and now we can just solve for phi, meaning that alpha is nothing but phi. So this angle alpha up here is actually phi, though that was easy to see. That was just a little one-liner actually, or two-liner you could say, that's a two-liner. With that out of the way, we know that 180 degrees pi is made up of 2 times phi plus theta. But here's one little thing we have to take into account. Either you can say that our y prime length is going to be in the negatives, so that's one way to look at it. What you can do, you can say we are going to take this angle down here clockwise. Meaning this angle down here is not pi, it's actually negative pi. Meaning our theta is then negative pi plus 2 times phi. So that's one way to look at that. There are many ways to look at something like this right here. So, meaning if we take a look at this right here, so our point P prime is for example here, then we have this angle theta right here, we have another right triangle right here. Our P prime is consisting of an x prime and a y prime coordinate. Also, this line right here that connects our point P prime and the center right here is our radius rho. Meaning P prime is nothing but, just like before, cosine of theta times rho is nothing but x prime. And we have the same speed with the y prime coordinate, just with a sign right here. So rho times the sine of theta is nothing but y prime. Now we can plug this chunk into here. So we are going to get, okay, we have a common factor of rho. Then we have the cosine of negative pi plus 2 times phi. And then we have the sine of negative pi plus 2 times phi. One cool thing is that we can, for example, choose the exponential definition of cosine and sine. Then you can factor out e to the negative I times phi, or you can say that the cosine is nothing but the real part of e to the I times this argument up here. Anyways, what you are going to get, this right here is just a shifted cosine wave, meaning up here in the x prime coordinate we are going to get negative cosine of 2 times phi, and down here we are going to get negative sine of 2 times phi. You can bring this negative sign to the front if you want. And here, now we have basically found out where our point P is all the time in our initial coordinate system. Now we can just solve for our x and y vector right here. We can substitute this in. And yeah, you are probably triggered at the moment. We can use double angle formulas for this right here. Bear with me for a second. I have one last thing to add. Right now, our cardioid is going to look like this right here. where our cusp, the singularity of this curve, is not going to be at the center. So right now our circle is lying somewhere here, I really don't know, but it's not at the center. Our cusp is lying at the point, well, rho and 0, you could say. So what I would like to do is do another coordinate transformation, meaning I would like to bring this coordinate system rho units to the right to get our cusp at the center. And then we know where our point P, let's call it P hat for example, then it's going to be all the time in this last and final coordinate system. So we are nearly done deriving this piece of shit right here. So just the last few things to add. So like I said, we want to shift our coordinate system now rho units to the right and 0 units up or down. Meaning we are going to go from this right here to this right here. And it's way easier to calculate the area and stuff like this using this form right here. That's why I'm doing this. That's the only purpose. Meaning, here in this coordinate system, we basically shifted our cardioid rho units to the left. But what does that mean for our coordinate system? We can just leave this cardioid stationary and shift our coordinate system rho units to the right. Meaning, our A, this time our shift is going to be rho and our B is going to be 0 in this case. I hope you can see where this came from. Meaning, initially we had, for example, this point P right here in this coordinate system, but now we are going to have a different point, P hat for example, with an x hat and y hat coordinate. How can we construct our point P hat? Well, it's nothing but xy minus AB, okay? So you see that that's actually quite easy. So that means this is nothing but xy minus, okay, and AB is nothing but rho and 0. We can actually bring this common factor of rho to the outside because 0 times rho is nothing but 0, so that works. So negative rho to the outside, we're going to get xy minus rho 1 0. Rho is 1 0. xy is nothing but this right here. We have a common factor of negative rho. So actually what we can do to construct our p hat right here, we can just add this factor here, what we just did, meaning we can just bring this 1 0 vector to the inside. So all we are doing is add a 1 right here. Now I would like to take a look at the double angle formulas right here for the cosine and sine. We have the cosine of 2 times phi is nothing but cosine squared of phi minus sine squared of phi, and we can make use of Papa Euler to turn this into 2 times the cosine squared of phi minus 1. If we plug this chunk into here, this negative 1 and this positive 1 are going to actually cancel out. So that's really quite good. We get rid of this factor of 1 right here. Also, the sine of 2 times phi can be expressed as 2 times the cosine of phi times the sine of phi. And we can plug this into here. And I want you guys to notice that we are going to have a common factor of 2 right here. So let's bring this 2 to the outside. And I'm going to write everything out. So one step after another. P hat. Our final coordinate thingy is going to be 2 times rho times this cosine of phi vector, or not over, that's so ugly, sine of phi, and then negative 2 times rho times, okay, we are going to have the cosine squared of phi, but this is cosine of phi times the cosine of phi, okay, let's put it that way, and then we have the sine of phi times the cosine of phi. One cool thing is that we have a common factor of 2 times rho, which is a common scalar right here. So 2 times rho. Then what we have is a common vector which consists of cosine and sine right here. So you see, this is our common vector right here that we have on both terms. Cosine of phi and the sine of phi. After factoring everything out, what are we going to end up with? Well, we have factored out this thing right here. So this makes 1. Okay, we have factored out this vector and this thing. So that makes a 1 minus Okay, we have factored out to rho and we have factored out this thing. All that's really left is this common factor of cosine of phi. So if you want, you can just bring this cosine of phi to the outside as a scalar and it wouldn't change anything. Okay, if this is more to your tastes. Et voila, we have found out where our point p hat is going to be in this final coordinate system all the time, and that's really good. And we have this chunk times some scaling factor, which are nothing but, well, polar coordinates, and that's really good because we know how to integrate polar coordinates. That's a really easy feat. One last thing I would like to do is to calculate our radius r, meaning if we go into the center of this cardioid, how long this line r is going to be all the time in this cardioid. So, you know, polar coordinates give us the chance to use Papa Pythagoras, meaning r squared is nothing but, well, x squared. In this case, we are going to have x hat plus y hat squared. Now we can just take the square root, the positive square root. Lengths are defined positives, in the positives, otherwise you wouldn't have a real metric. And here, this right here is just our r, meaning our r is nothing but the square root of. Okay, you can just take those individually squared, meaning we are going to end up with, or you can just break it up into this x and this y coordinate. Okay, it really doesn't quite matter how you do it. It's the same procedure every time. So we have 2 squared, rho squared, 1 minus cosine of phi squared times, okay, then we can factor this stuff out. That's a common factor on all of those. Then we have the cosine squared of phi plus sine squared of phi. All of this in the square root. If we take the square root of this chunk right here, well, we are going to end up with something in the absolute values. I'm terribly sorry. So if you take the square root of something squared, it's the absolute value of that thing. Okay, 2 is positive, meaning square root of 2 squared is nothing but 2. Rho is positive all the time, meaning the absolute value of rho is going to be rho. 1 minus cosine of phi, okay? Cosine of phi is between -1 and 1, so either way, 1 minus cosine of phi is going to be between 0 and 2 in this case. So that right here is actually positive, so this is 1 minus the cosine of phi. Cosine squared plus sine squared is nothing but 1, so square root of 1 is nothing but 1. So that right here is our r. And, well, we actually need this right here to calculate our integral. There was a lot of work. There was really a lot of work, and I shit you not, guys, that's my 6th attempt to record this video right here. I'm spending ages on it, and I just hope that it's going to be worth it, that at least 2 people are going to watch this video. Let's go for the integral. Whew. So let us go for the last thing to do on our list. We're going to calculate the area under this cardioid curve. And like I said, the good thing is we're dealing with polar coordinates just with a little scaling factor. Meaning, in general, we can, in the 2-dimensional case, construct our area as nothing but a certain double integral over a certain region, let's call it D. Then we have the Jacobian determinant right here, times a little area piece. Okay, and it really depends. Our area piece right here is going to be dr d phi. In this case, we are defying the system of mathematics once again, because we are dealing with polar coordinates. And trivially, our Jacobian determinant is just going to be r, because we are dealing with polar coordinates. So this reduces quite nicely. So we are going to have double integral of some sorts, r dr d phi. Our outer integrals with respect to phi. What is our phi? Well, obviously we are going to make one whole turn until we complete this area, meaning it goes from 0 to 2 pi. What is our r? Well, at first we are going to start with a radius of 0, so let's just assume this, and we are going to go up until this part right here, our radius at any point of time. So 2 times rho 1 minus the cosine of phi. That looks quite weird as an upper bound. And here's one thing to notice. That's not the trivial part. You can just use Fubini, for example, and break this up into an integral over phi and an integral over r, because we have to integrate with respect to r at first, just because our upper bound is with respect to phi. So this is r with respect to phi. So let's evaluate our inner integral at first and then our outer integral. Trivially, r integrated is just r squared over 2. So we are going to end up with an integral from 0 to 2 pi of r squared over 2. And then we are going to have this from 0 to, well, 2 times rho, 1 minus the cosine of phi. Integrated with respect to phi. The lower bound is trivially just 0. I'm saying trivially way too often right now. So this is just going to go to 0. And up here we can just plug the chunk in. Okay, just step by step. So we are going to have integral from 0 to 2 pi of, and this is going to give us 4 rho squared over 2. 4 and 2 is going to cancel out to just 2 rho squared. And then we have 1 minus the cosine of phi squared d phi. That's a scalar. We can bring it to the outside using the linearity of the integral. Also, we can expand this right here into 1 minus 2 times the cosine of phi plus cosine squared of phi. And then we can easily integrate this. So we are going to get 2 times rho squared. Using the linearity of the integral, we can break this up into 3 separate integrals. So the first one is going to be 0 to 2 pi of just d phi. Okay, 1 integrated and then d phi. So you see where this comes from. Then we can bring this factor of -2 to the outside. So -2 times the integral from 0 to 2 pi of the cosine of phi d phi. And the last one is going to be the integral from 0 to 2 pi of cosine squared of phi d phi. We can either integrate this or we can argue geometrically, in geometry ways. Never mind. We are going to do the integration step by step. So this right here is going to be just phi from 0 to 2 pi is going to vary to 2 times pi. This right here is going to be, well, cosine integrated is nothing but sine of phi from 0 to 2 pi. Sine of phi from 0 to 2 pi, okay, sine of 0 is 0, and sine of 2 pi, well, it's periodic in pi, so that means this whole thing is just 0. This cancels out quite nicely. What about this thing right here? You can do integration by parts. You can take the real part of the complex exponential function, or we can just rewrite this using the double angle formula, because you know the cosine of 2 times phi was nothing but 2 times cosine squared of phi minus 1, and now we can solve for cosine squared, so this is 1 plus and then over 2. And well, that's an expression for our cosine squared of phi. So this is something that works out quite nicely actually. Why not plug this in? At first we are going to have this part. This is 4 times pi times rho squared. And then we have 2 times rho squared, distributing this into everything. So plus 2 times rho squared. Then we have an integral from 0 to 2 pi of. Then we are going to get 1/2 plus 1/2 times the cosine of 2 times phi d phi. Up to the next blackbird. So we can break this up once again using the linearity of the integral. 1/2 integrated with respect to phi is just going to give us, well, 1/2 times phi from 0 to 2 pi. So that's 4 times pi times rho squared. Then we are going to have plus 2 times rho squared. Like I said, this is going to give us 1/2 times phi from 0 to 2 pi, which is just going to vary to 2 pi once again. We had this situation before. Then we have plus 1/2. We have this chunk once again, 2 times rho squared, and it doesn't quite matter, to be honest, if we drag this along. And then we have the integral from 0 to 2 pi of the cosine of 2 times phi d phi. What is this going to vary to? Well, you might ask this yourself, maybe you don't. Cosine of 2 times phi integrated is nothing but 1/2 times the sine of 2 times phi from 0 to 2 pi. Sine of 0 is just 0, so this is going to vanish, so that's already quite good. Then we are going to get sine of 4 times pi. Once again, sine is periodic, and pi, or something like this, meaning this whole thing is going to go to 0. That's why I said it really doesn't quite matter if we drag the scalar along. Meaning, this 2 and this 1/2 is going to cancel out. In the end, we're going to get 4 times pi times rho squared plus 2 times pi times rho squared is going to evaluate to, okay, let's do the algebra a bit more. We have a common factor of pi times rho squared, okay, this is pi times rho squared times 4 plus 2. 4 plus 2 is nothing but, well, 6. No, I'm not going to do the piano axiom crap right here. I'm just going to go along nice and easily. Oh no, never do this. Never put the number to the back. It doesn't look aesthetic. It just doesn't. So this is 6 times pi times rho squared. And this is the area of our cardioid curve. Yes, exactly. And then we're done. That was such a long video once again. Let me see how long this video recording session actually goes. Oh boy, 54 minutes. Always those long sessions. I hope you did enjoy this video. If you did, please like and subscribe to my comment channel if you like. Don't forget to check out the new merch. You still get 15% off everything in my German spreadshirt shop and my Teespring shop. Recommend this channel to your friends, to your family, whatsoever. Don't forget to spend a lot of time with your loved ones today. It's Valentine's Day. Don't spit them in the face. Don't slap them. Cuddle them. I'm going to cuddle with my girlfriend too today because I really love my girlfriend. Lisa, I really love you. I hope you're going to stay with me forever. Yes. What else can I say? I hope you did enjoy this video, and up until the next video, have a Flammy day, my boys. See ya.